Okay, so in this question you've got two spheres, P and Q, and a horizontal table. So we're going to have a little diagram, alright? So we're going to have P here, and Q over here. Mass 5 kilograms and 3 kilograms respectively, okay? Rest and smooth table, they are connected by a light and extensible string which is initially slack, okay? So the string is slack. And it says an impulse of magnitude 1.2 Newton seconds is applied to Q in the direction PQ. So basically, this is the direction PQ, isn't it? When it says PQ, because it's talking about the line segment from P to Q. So it's horizontal. So an impulse is applied, okay, to this sphere Q in the direction PQ. So we're going this way. So the velocity, in fact, then will be going here. So it says then, doesn't it, in part A, determine the speed with which Q begins to move. So we can call that, say, V, in terms of working out then its speed. We know it's going in that direction because the impulse is acting in this direction, PQ, and the impulse is, as it says, 1.2 Newton seconds. Okay, so our focus in part A is quite simply to focus on Q, what happens in Q. And of course, they've given us the impulse, okay, acting on Q, and we just need to remember the fact that impulse is essentially the change momentum, right? So we're looking at the change in momentum of Q, right? Our focus is on Q. So we know the impulse is 1.2. Change of momentum then is momentum after, take away momentum before. So the momentum after, don't forget with momentum, yeah, it's just going to be mass times velocity, isn't it? So the momentum after the mass of Q is 3 kilograms, isn't it? So it'll be 3 for the value m times then velocity v, and we've called it v. Take away then the momentum before. Okay, that's the change of momentum. Momentum after, take away momentum before. And momentum before, of course, is going to be 3 times, and the velocity was 0, isn't it? Because it's at rest, it says. So 1.2 equals 3v, okay? So we can use our calculator, and when we get v out then to be 1.2 divided by 3, so that implies v is 0.4 meters per second, okay? So that's what the speed it begins to move at. Part B then, it says, find the speed with which P moves after the string tightens and determine the impulsive tension in the string. Now, with this, it's important to consider two diagrams, okay? You need to look at the situation before and the situation after, right? And the situation before, quite simply, is as the string tightens, okay? Literally at that particular moment, okay? As that string tightens, right? Now, of course, velocity of P as the string tightens is still going to be 0, isn't it? It hasn't moved, right? But the velocity of Q is going to be what we worked out in part A. It will be still moving at 0.4 meters per second, okay? Literally on the point of it tightening. So this is sort of like the consideration before, okay? We then need to consider then the situation slightly after, right? And we're literally talking instantaneous seconds here. So again, the string is taut, okay? But this time, now, Q will have a different velocity because P is going to be set in motion, okay? So we can call the speed after then, well, we called that V before them, so we can call this maybe V1, right? And call that V1 as well, right? Because if you think about it, when the string tightens, okay, it's going to sort of have an effect on Q. It's going to sort of slow it down a bit, probably, okay? And it continues, but P will have exactly the same speed as Q because they're connected by this string. The string is taut, so they're going to be going at the same speed, aren't they, for this string to be constantly taut, right? Same speed, so they set off them in both V1. So all you've got to do is use the conservation of momentum, okay? So we say, look, by principle of conservation, okay, of momentum, momentum before equals the momentum after, isn't it? Or the momentum after equals the momentum before. The momentum, let's look at the momentum before to start with. We've got this here, so remember the mass of this is 5, so 5 times 0 plus the momentum of this, which is the mass is 3 times 0.4, so this is just as the string is getting taut, will equal the momentum slightly later than when this is obviously on the verge of moving with speed p1. So the momentum here will be 5 times v1, because the mass of this is 5, add then this one there, 3v1. Okay, so you can work this out. That becomes, of course, 1.2. This becomes 8v1. Okay, 5 and 3 is 8, so then divide that by 8 then to get v1. Okay, so 1.2 divided by 8 is 0.15 meters per second. Okay, and it says then determine the impulsive tension in the string. Okay, well, impulsive tension in the string can be had if we just look at the change in momentum, okay, that's taken place on one of these objects. Okay, now it's up to you what object you want to consider, but I would go for the one that was stationary to begin with. So if we focus on P, okay, and look at the change of momentum of P, change of momentum, well, that would be the momentum after, so that would be the mass here, which of course was 5, wasn't it, times velocity of it after, which is 0.15. Take away then the momentum before, which is mass times, of course, then 0. So you've got 5 times 0.15, and that comes out to be 0.75. Okay, and of course, momentum, then you've got the change of momentum of P, which is also, remember, equal to impulse. So if you remember, change of momentum is the same as impulse. So the units are going to be Newton seconds, but the change of momentum of P is then equal to the impulsive tension in the string. Okay, so we can say straight away then the impulsive tension in the string equals to 0.75 Newton seconds, because the effect it has on P is what's going on in the string. Alright? Okay, that's the impulsive tension that's taking place in the string to have the change of momentum of P. Okay. Part C then, it says calculate the loss in energy when the string tightens. Well, quite simply, we need to consider what sort of energy is going on here, where we've got kinetic energy, haven't we? Okay, so the kinetic energy before, essentially, and the kinetic energy after. Right, so that's all you've got to do. Now the kinetic energy before, remember kinetic energy formula is half mv squared. So it'll be half times 5 times 0 squared, plus half times 3 for this mass times 0.4 squared. Okay, so that would be, well, that's going to be 0, that's going to be wiped out, and that's going to be 0.24. Okay, remember energy is measured in joules. Energy after, half times 5 times, well, that's going to be 0.1 now, squared, plus half times 3 times 0.15 squared. Okay, so they're both moving the same velocity. We get 0.09, so then the change in energy, the loss in kinetic energy, you can see there's more energy before because that's 0.24. 0.24, take away 0.09, which is 0.15 joules. Okay?